This is part 1 of a video going over topics covered in Unit 4, Unit 4 being the unit covering exponential and logarithmic functions. So this first video is really going to concentrate on inverses. So let's talk about that. So first of all, what does an inverse do? Well, an inverse, as many of you stated, undoes a function. And kind of getting more specifically, with a function that's inverse, the domain and range completely switch. An inverse of a function takes the range and brings it to the domain of the original function. So domain and range should totally flip when you're talking about a function and an inverse. When does a function have an inverse? Well, in order to be invertible, the function has to be one-to-one. So you hear that you'll hear that expression a lot, one-to-one, to be invertible. Well, what the heck does that mean? It means that every x value has to go to a unique y value. In other words, nothing should be repeating. So let's consider a function that breaks that rule. F of x equaling x squared. Well, this is a function. We've worked with functions like this a lot. This type of quadratic or very simple parabola. But if we think about a couple points here, f of 1 would have an output of 1, but so would f of negative 1. And you think, well, what's the big deal? Well, the problem is when finding an inverse, the x and y values, or the domains and ranges, are changing. So if we did that, 1, 1, of course, would still be 1, 1, but then I'd also have 1, negative 1 as a point on the inverse. And that's a problem because that's no longer a function because you have x going to more than one output, a given x value. So, and you need an inverse to also be a function. Okay, so another way to see that, let's stick with the same function. Another test, if you have a graph, to see if something is invertible is the horizontal line test. Remember, to be a function, it has to pass that vertical line test, which means any line you were to draw, any vertical line, it would at most cross the function once, to be the graph once, rather, to be a function. Well, the same idea as with the horizontal line test. This is not invertible because notice there are many horizontal lines, infinitely many, that I will draw that are crossing the graph more than once. So that's a problem. It means y values are repeating, so not invertible. That being said, well, I could actually put a restriction on a function like this to make it invertible. For example, if I said, is this function invertible, f of x equals x squared for x greater than or equal to 0? Well, yeah, if we look at that piece of the graph, that part of the domain, yes, that part of the domain makes it so that I have a graph that is one-to-one and thus invertible. So you often will see an original function not be invertible, but then you can perhaps use a restriction so that it is invertible. Okay, so now let's talk about, all right, here's a function. That's, once we determine it's invertible, how do you find an inverse? Well, we just talked about how a function and its inverse, the domain and range switch. So to find an inverse, you can switch x and y and solve for the new y, and we'll do a practice shortly. How do you prove two functions are inverses? So to prove f of x and g of x are indeed inverses, to officially prove, you would do the composition both ways. And again, a function and its inverse should undo each other. So you should get x when you do that composition. And when you go the other way, it should also result in x. So that would be proving that two functions are inverses. In terms of the symmetry, remember you're switching x and y to solve for its inverse. So a function and its inverse are symmetric across the line y equals x, which makes sense, again, switching x and y. All right, let's do, now that we've done that, let's do, talked a little bit more broadly about inverses. Let's find an inverse and domain and range of each. So let's do 2 examples here. So let's do example 1. So here's a function, and it's a rational function, something we just did not long ago. So actually, let's do the domain and range first. So the domain is easy. The domain denominator can't be 0, so we can't have x being -1/2. So negative infinity to -1/2, union -1/2 to infinity. The range is a little trickier, and as always. So either you could try to find the range here, or we can find the inverse and find the domain of the inverse, because remember, the domain of the inverse will be the range of the original. But one thing I notice here is, if going back to the fact that it's a rational function, it's going to have a horizontal asymptote at y = 5/2, because you've got the degree of the numerator and denominator the same. So you take the coefficients, and it'll be that horizontal line, y = 5/2 in this case. So I'm going to suspect that the range here is going to be everything but 5/2, thinking it's not going to cross that EBA. But we're going to come back, and I will confirm this when I find my inverse. So now finding the inverse, switch x and y, and let's solve for our new y. So we got to get that 2y + 1 out of the denominator. So 2xy plus x equals 5y - 7. And remember the algebra associated here with solving for y. You're going to bring everything with y to one side and everything else to the other side. And then factor, whoops, what happened to my y here? And then factor out a y. So my inverse, my f inverse of x, is equal to -x - 7 over 2x - 5. Okay, and let us double check some things. So the domain here is everything but 5/2. That's where the denominator is 0. So my hypothesis is correct here. So again, if you were unsure about the range of the original, when you find the inverse, the domain will be that range. And it makes sense. Again, we talked about that horizontal asymptote for the original function at y = 5/2. Now for the range should be the domain of the original, meaning everything but -1/2. So let's look at our inverse and see if that makes sense. So looking at my inverse here, the degree of the numerator denominator is the same, so I would take the coefficients for the EBA. So it'd be y = -1/2 as the EBA. So it does make sense. It not crossing that EBA, so the range being everything but -1/2. Okay, that was problem 1. Let's do another. This one with a restriction. So number 2, we'll call it g of x equals 3x - 1 squared plus 7. Now, this right here would not be invertible. A parabola would not be invertible, but I'm going to put a domain restriction on it to make it so. Okay, so the domain of this original function, I just gave it to you with the restriction, so -infinity to 1. And what's the range? Well, we've worked with parabolas before, so the range of this would be the smallest this squared piece is going to be 0, and then it's going to go to infinity, and then I've got the plus 7. So the range is 7 to infinity. Now when I find my inverse, we've got to keep this in mind. The domain and range should be totally flipped for the inverse. So keep this in mind when we find our inverse. So finding the inverse here, switch x and y. And we're going to solve for our new y. So let's subtract 7, divide by 3. So I've got x - 7 over 3 equals y - 1 squared. Now this is where the restriction comes into play, because if I want to solve for y - 1 by taking the square root of both sides, remember when you do that, it's always plus or minus. So it'd always be this when I'm solving for something squared, but it can't be both here. I mean, we're only having, this would not be a function if I had both. So which is it? Well, that's when we look back to our restriction and our original function. So the restriction this domain restriction, well, that should be the range of my inverse. So which, the positive square root or the negative square root, will end up having this range? Well, it's got to be the negative square root. So so continuing with this, I've got y minus 1 equals negative square root of x minus 7 over 3, and then add 1. So my inverse, G inverse of x, is equal to 1 minus the square root of x minus 7 over 3. And the domain and range should totally flip, and it does make sense that the domain of this should be 7 to infinity, and the range should be negative infinity to 1. So that checks out. So with the restriction, you've got to be, when you have a function with a restriction, that should come into play when you are solving for your inverse. You need to take that into account. Okay, and that is it, I believe, on the inverse talk.